this is a tutorial on stagnation properties, how we can evaluate stagnation quantities. So, we will just do few problems and try to understand what exactly do I mean. Okay. So, if I have a duct and at some cross section I have velocity V1 which is around 500 meters per second, and your T1 is 300 Kelvin. Assume air. Cp is 1005 joule per kg Kelvin, gamma is 1.4. So, what is the stagnation temperature? Okay. So, we need to find T01. So, we go back to the equations. T01 is T1 plus V1 square by 2 Cp. This we obtained from the enthalpy equation, the energy equation. Qs equals Ws plus H1 plus V1 square by 2. So, the process is, at any point we take the fluid to a location where the velocity is 0, so a state where the velocity is 0 isentropically without work. So, there is no heat in the process, no heat transfer, no work done, and we have done this isentropically. So, there is no loss. So, there are no losses. So, in the TS diagram we have state 1 which we take it to a state where V is 0, we know T1, we need to find T01. Okay. So, this is the imaginary process where it goes from 1 to 0. So, it is the mere substitution of this equation. So, your T01 would be just 300 plus 300 Kelvin plus 500 square by 2 into 105. This would be around 424 Kelvin. So, what we have done is we have taken the fluid which has some temperature going with some velocity. We have isentropically reduced that velocity to 0 with no heat and no work transfer, and that state is the stagnation state, and the temperature associated with that is T01. We also know the difference between T01 and T02 is V square by 2 Cp. So, if the fluid was moving with a different velocity, you would have got the stagnation temperature to be different. If the fluid is other than air, then again the stagnation temperature would have been different. Okay. That is what you get from this example. Now, we will extend this problem. So, there is some duct, I have V1 500 meters per second, T1 300 Kelvin and say T01 is 424 Kelvin. This moves to a new location 2. So, this is my location 1 and this is my location 2. So, this is question 2. If no work done by the system or to the system and no heat transfer, what is T02? That is the first question. What is T02 and what is V2 if I know my T2? My T2 is okay. So, the question is, I have a flow in a duct with at station 1 the velocity is 500 meters per second and T1 is 300, T01 is 424 Kelvin. What is my T02 if no work, no heat transfer? So, if no work, no heat transfer, I have T01, H01 equals H02. How did I get? From the energy equation where I assume this to be 0. So, I end up with H01 equals H02, which is nothing but T01 equals T02. Okay. So, my T02 is same as my T01. So, in the TS diagram, all this assuming 1D flow or quasi 1D flow. I have 1, I have 2, there is some process associated with 1, there is a stagnation state which has T01. Because there is no heat and no shaft work, the temperature is the same. Okay. So, the delta S is this, which is entirely due to your irreversibility. Okay. So, your state 1 and state 2 has the same stagnation temperature, okay, but the pressure associated with this is different. So, how do we find V2? Now, we know that T02 is the same as this, which is 424, Kelvin. This is also 424 Kelvin. So, your T02 equals T2 plus V2 square by 2 Cp. Now, you know all the values T02, T2, V2 and Cp. Substitute those, you should get T2 to be approximately V2. We have to find V2. 640 meters per second. Okay. So, I repeat the process here. I have state 1 and state 2. At state 1 we have velocity 500, state 2 we have velocity 640. Since there is no work and no heat transfer, the stagnation temperature is the same. So, we have equated the enthalpy and obtained our V2. Okay. So, this is nothing but your energy equation posed in a different way. Now I have a constant area duct. This is question 3. This is connected to a large chamber where the fluids are all stationary, it is not moving around. So, the quantity you measure here is the stagnation quantities. So, the pressure I measure here is P0 and the temperature I measure here is T0. Now, this chamber supplies air to this particular duct. So, if I assume the station 1 has the same stagnation quantities as the chamber, I have T01 and T01 same as this. Now, the fluid flows through the duct, and at location 2 I have P02 and T02. Okay. For some reason your T01 is not equal to T02 because of your heat transfer, assuming Ws is 0, no shaft work associated with this fluid that is moving through the constant area duct, but there is some heat transfer that is happening. So, what is the Q to keep this constant? What is the Q that you need to supply, or what is the heat transfer that is needed to keep your T01 same as T02? So, what is the process in TS diagram? So, I have 1, I have 0.2, the 1 has a stagnation state T01 and 2 has a stagnation state T02, which is now different. So, from the energy equation, Cp T01 plus Q equals Cp T02 plus Ws. Now, Ws is 0. So, here Q is nothing but Cp into T02 minus T01. So, depending on the values of T01 and T02, you would get your this thing. Suppose if I assume T01, T02 to be T02 to be say 300 and T01 to be 500 multiplied by value of Cp, which is 1005. This is minus 20100 joule per kg. So, this is a minus sign, which means Q is in this equation, Q is the heat supplied to the system. So, now it is a minus sign, which means heat is lost. So, there is heat that is Q lost, which is approximately 21 kilojoules. Okay. So, lost heat is 201 kilojoule, that is why it comes with a minus sign. So, if I have a duct that which has the stagnation quantity at the beginning, now you are going to lose this stagnation temperature if I do not account for the heat transfer. So, you need to insulate the pipe if you want to keep the stagnation temperature same. Okay. Now, if I you can now reverse the question. I supply some heat here. What would be the velocity that you gain at the station 2? So, if I have this 1 and 2, if Q is, so let us take 0.1 kilojoule per kg with a minus sign. So, I have T01 to be 300 and now what is my V2? So, from this equation I can find, so this is my question 4. So, from this equation I can find T02 which would be okay. Find your T02. Once you have T02, you can find your V2 if I know my T2. Okay. So, let us assume T2 to be some value. T02 is 300. So, let us put 200. Okay. So, you can find your V2. T01 is 500. T01 is 500. T02 you would get as 300, which is same as our numbers in the previous question, and then Q is this, again the same number as from the previous question. You can find your V2. So, there is a delta S that is happening between process 1 and 2. If the delta S is there, then we have also seen the change P02 by P01 e power minus delta S by R. Since delta S is always positive, your P02 is always less than P01, which means the P0 here, P01 and this is P02, P02 is always less than P01. So, if I conclude today's lecture with the following understanding. So, I have the TS diagram. For any given state, there is an associated stagnation state, which is an isentropic process. So, you bring the velocity isentropically to an imaginary state where the velocity is 0, and you call that as your stagnation point, and associated with that you have T01 and P01 and the other stagnation quantities. Now, for process 1 to 2, associated with 1 you have stagnation quantity T01 and P01, associated with 2 you have a imaginary state where your stagnation quantity is P02 and T02, which need not be the same, okay. But this imaginary process of taking this point to the stagnation point is isentropic process, but from 1 to 2 the end state stagnation points are different. Now, if I assume no heat transfer and no shaft work, then my 1 to 2 has same stagnation temperature. This is 1, this is 2. So, the imaginary process at which state 1 is taken to the stagnation point will have T01 and P02, that is an isentropic process. Likewise, you have state 2, with that you have a stagnation state where you have T01 and T02 and P02. Since there is no work and no shaft work, your enthalpy is same from the equations which we have seen. H01 equals H02, where Q and Ws is 0, and because of that we have a temperature T01 and T02 same, but the pressures are different. Okay. Now, if I also assume my losses to be 0, no Ws and no losses. Okay. So, in the TS diagram, this is all in the TS diagram. Process 1 will have a stagnation state, is taken to a state 2 isentropically, okay, with no shaft work, no heat transfer and no losses. This state 2 will have the same stagnation point. So, the T01 and T02 will be the same, and my P01 and P02 will also be the same, because my P02 by P01 is e power minus delta S by R, where delta S is now 0. If that is 0, then my P01 and P02 are same. So, this graph modifies to this. Okay. So, this is the stagnation process. This is the process between 2 points where there is some heat, some shaft work and some irreversibility. This is no heat, no shaft work, but there is some irreversibility that is associated with the process, and here we have assumed even irreversibility to be 0. So, the process is just this with no entropy change. So, if I have a pipe between point 1 and 2, if I assume no losses, this is the process that is going to happen with no heat and no shaft work. Okay. With that, we conclude today's tutorial and the concept of stagnation properties. We will discuss stagnation pressures later, but what we have demonstrated now is to find how to find the stagnation temperature and the basic concept behind the stagnation process.